Hi, my name is Nardi. I'm a PhD student at the University of São Paulo. My advisor is Professor Cibelle Celestino Silva, and my work is entitled The Mathematization of Electrostatics in the 18th Century. So, first things first, I will do the introduction to my work. I will show our philosophical framework that we use to analyze our case studies. I will present my research questions that drive my research. And then we will go through the historical cases themselves, which are Johann Albert Euler's theory of data for electricity, I. Pinus' theory for electricity, and Coulomb's theory and mathematization. Then I will conclude our study, and furthermore, I will make some considerations about entangling history and philosophy of science. Well, the mathematization of electrostatics is illustrated and usually oversimplified in textbooks by the eponymous Coulomb's law, which is this one, that the force goes as the inverse of the square of the distance. We will get to Coulomb, but first I will discuss the mathematization by focusing on the use of mathematics in different theories of the time on the same topic, electrostatics, but prior to Coulomb's works. I am defining mathematization here following the literature, which is in this case represented by Jinka's article, What Did Mathematics Do to Physics, from 2001. In that article, he distinguishes quantification and mathematization of a physical theory. Quantification is the use of numbers in a physical theory, and mathematization is the production of abstract mathematical formulae, geometrical and/or algebraic. So those two things are different. They are not a dichotomy, but they are different. He also defines what is a mechanistic explanation, which is an explanation that depends on tangible objects and contact forces. Those three definitions we use in our work, in our historical work. There are many possibilities for the application for philosophical studies on the application of mathematics in physics and in science in general. We here chose the inferential conception, also known as mapping account, because it resonates with our own experience with primary sources, so that's why we chose it. And to explain it simply, in simple terms, the inferential conception is mostly this. A scientist usually has an empirical/theoretical setup to study a physical phenomenon, This empirical/theoretical is built up by observable entities and non-observable entities, from molecules to forces to things that are clearly observable, and so on. The scientist makes a context-dependent choice from the empirical setup to the mathematical model that most conveniently can be used to explain or to describe or to represent the empirical/theoretical setup, which is the initial part of the work. And this movement from the empirical theoretical to the model is called the immersion step. In the mathematical model, the scientist makes a derivation step, which is just following the rules of mathematics and logic. And when he gets to the results, which are here, he goes back to the empirical theoretical setup, of course, by the interpretation step. So there are three steps: immersion, from the empirical/theoretical setup to the model, he makes a derivation, and then he goes back to the empirical/theoretical to make further physical considerations about the phenomena. However, there is a warning here. In the inferential conception, mathematics has no explanatory role per se. However, since our historical actors clearly deem mathematics as explanatory, we will have to describe mathematics as explaining electrical phenomena. So this is a choice we are making between the the language of the philosopher and the language of the historian. We are going with the language of the historian here. Our research questions are thus these. Did the mathematization in these studies in the 18th century have different approaches? And what factors counted in shaping the mathematization by different historical actors? Well, the historical cases. First, Johann Albert Euler's ether. Johann Euler, which was the oldest son of mathematician Leonhard Euler, wrote two works on electricity. One in 1757 and one in 1759, called Recherche sur la cause physique de l'électricité. In the first one, he describes his theory as an ethereal theory, where ether is an elastic and subtle fluid that permeates all bodies. And in his first work, there is no mathematization, no production of abstract mathematical formulae. In his second work, 1759, he does mathematize his ethereal theory using concepts that were common to the study of hydrodynamics at the time. So here we have an example of Johann Euler doing mathematics in his 1759 work. Here we have a pore of a body, which is this ABDC channel. That's where the ether is stuck. That's where the ether moves from AB to DC. And there are many cross sections here: AB, PM, A prime, B prime, P prime, M prime. He makes some physical considerations about the ether, which creates these two equations here that he needs to solve simultaneously. The first one comes from the movement of the ether from AB, PM to A prime, B prime, P prime, M prime, and the second one comes from Newton's second law. So these two equations are approximate equations for the ether moving in a pore of a body. And he solves these two equations, and here's the solution, which is this exponential. And phi is the density in PM, the density of the ether in PM. P is the density of the ether in AB. Omega and gamma, the velocities. And density is related to a concept he calls elasticity. So in this case, he mathematically proves a relation between the velocity and the elasticity of the ether, where the velocity is higher, elasticity is lower. And elasticity here is a concept, like I said, is a concept that is related to the density of the ether, so phi and pi, and it's akin to our concept of pressure. So it's like our pressure. In modern terms, we can say that where velocity is higher, pressure is lower, and in the equation is just a constant. We can see Johann Euler applying his mathematical result in this case. In this example, a body A positively electrified and a body B is in its natural state. So we have one positive and one in the natural state. And here, positive for Johann Euler, positive means that the elasticity inside A, the elasticity of the ether inside the body A is higher than in the rest of the experiment, air and body B. So in his 1759 work, the body B receives the ether that flows from A to all space. In C, the shortest line between A and B, the ether finds less obstacles and ends up accelerating. His velocity increases. Thus, the elasticity drops, as proven mathematically, and elasticity works just as pressure. This creates a force that throws A towards B, B towards A. So they approach each other. One moves towards the other. In his 1757 work, Johann explained the same case, and the explanation is similar, but there's no mathematics. He just uses a hydrodynamical reasoning. We see that the relation from the preceding slide is used to explain the phenomenon. However, it is not essential. In his 1757, he explains the same phenomenon with no mathematization. This contrasts with the next historical case, which is Franz Apin's mathematical electric fluid. So they are in direct contrast in their use of mathematics. Hypinus theory for electricity comes mostly from his 1759 work, Tentament Theoriae Electricitatis e Magnetismi, published in the Russian Empire. Hypinus theory is based on Benjamin Franklin's one electrical fluid. In it, all bodies have a natural quantity of fluid, and excess of that fluid is the positive state, and a deficiency, the negative state. Hypinus also uses the Newtonian concept of action at a distance, something that was nowhere to be found in Franklin's work and in Johann Euler's work, for that matter. In Hypinus theory, there is no ether. His approach to mathematics differs from Euler's one. We can see his way of doing mathematics in the following slide. One of the first things that Hypinus does in his book is to construct what I called a physical-mathematical hypothesis. Here we have this theoretical scenario where A is a body that can be electrified, and B is a constituent particle of the electric fluid touching the surface of A. So we have A and B. A has a natural quantity of fluid of value Q, and in the case where A is in its natural state, he defines some sort of primitive repulsive force, which is the force exerted by the electrical fluid of A on B when A is in its natural state. So what he does here is to correct the value of the force between the whole body A, electric fluid plus the ordinary matter, on the particle B. And for this, he adds an excess alpha of fluid on A, inside A, distributed uniformly. So we have these symbols, alpha, Q, R, and the total force. And in his calculation, the total force is just alpha divided by Q times this primitive repulsive force, R. With this, he can already start explaining and defining the electrical attraction and repulsion. When alpha is an excess, it's defined as positive. So the force is positive, and it is defined in this way as attractive. When the body B is deficient in electric fluid, that is, when A is in the negative state, then alpha is negative. The force F is negative and thus needs to be repulsive, since the positive was defined as attractive. This is just between a body and a particle, but he can generalize it for the interaction between two different bodies, body A and another body B, not just between a whole body, electric fluid plus common matter, and a particle, but also body to body. Another interesting thing he does in his book is the explanation of the Leyden jar, which was a very important phenomenon at the time, one that Benjamin Franklin tried to explain with his own one fluid theory. And here the Leyden jar in Hypinus construction looks like a capacitor or condenser. We have a metal plate CD connected to a generator through a wire TS, and we have a metal plate IK grounded to earth through the wire LM, which is a metal, just like TS. And if someone uses the generator, it's gonna pump up some electric fluid inside CD, which gets an excess alpha of fluid. And this excess alpha fluid is gonna repulse the particles of the metal plate IK in the other side of the experiment, and creating thus a deficiency of value beta inside IK, since the particles of electric fluid in that metal plate will start to run away from IK to the ground through the wire LM. And this flow of particles out of IK will continue, or would continue, until beta increases enough to zero the force of the whole apparatus inside the particles of electric fluid of IK. When that force zeros, the particles cease to flow through LM, and Hypinus obtains some sort of criteria for the electrification of the jar. The criteria is beta equals alpha R prime divided by R, and R prime here is not the derivative. It's the repulsive force exerted by the plate CD in its natural state on the particles of the electric fluid in the surface of IK. And in this case, the mathematics is clearly central to the explanations. He derives a mathematically calculated criteria for the electrification of the Leyden jar, something Franklin didn't do. We can see the same thing, the same reasoning that we saw in Hypinus' case in Coulomb's treatment of mathematics. Here we have an example of Coulomb doing mathematics, and it seems to be just like Hypinus dealing with mathematics. Here we have a cone trunk, this one, A, B, and P, and Coulomb describes the relation between an infinitesimal force dF and a distance x, where x is Cp, just something like this. And m is a constant in his calculations. So with an integral and some boundary conditions, he calculates the relation between the force and the distance x. And here in this case, he's not using the relation of the force being in the inverse of the square of the distance. He's generalizing it. He's making the force in relation to the inverse of the distance to the power of 2 plus n. And if you make the calculations and you put n bigger than 1 and a constant, equals to 0, then f explodes. It tends to infinity. If n is bigger than 1, this means that the closest parts to each other are the only parts that electrically interact repulsively or attractively with each other. If n is smaller than 1, then f does not explode to infinity. And that means that all parts finitely close to each other electrically interact among themselves. So they just need to be finitely close. In n bigger than 1, they need only the closest parts, infinitesimally close, are the ones that interact with each other. And he applies this calculation in the case of a conductor of an unspecified format, of an unspecified figure. In this case, we have n equals 0, that is, the force is the inverse of the square of the distance, and Coulomb deducts that the electric fluid in a conductor AAFB will flow towards the surface and will leave the interior of the object. Because well, all parts of the electric fluid of the body will electrically interact with the fluid. Since if the conductor in this case is full of fluid, excess of fluid, then all parts of the electric fluid inside the conductor will repel each other. And since they can interact, because n is smaller than 1, is 0, then they are going to repel it, and they are going to run away from each other as much as they can, which means they all go towards the surface. So in any given point, like the point B, they go towards the surface. However, his deduction here works for a one fluid theory, just like Hypinus and Franklin's theory, but not for the two fluids theory. That's not clear from his calculations. And that's what he actually believed. He was a two fluids theory believer, not a one fluid theory. This one versus two fluid theory is a mechanistic question. It's also a physically relevant question at the time, and it doesn't pull Coulomb's attention at all, because he was focused on a mathematical explanation for the phenomena, which is why are there no signs of electrification inside a conductor. As conclusions, well, we can see that Hypinus' style of mathematization depends on the intertwinement of the empirical world and the mathematical structure, which is algebraic in his case. And this we can clearly see the inferential conception here. It goes from empirical world to mathematics and then back to the empirical world again. The explanation arises on his jumping to and from mathematics. In the electrification of the Leyden jar, a mathematically calculated relation is at the center of the explanation. And then he goes back to derive some possible experiments for the Leyden jar based on the difference between beta and alpha, the excess and the deficiency. Hypinus can place his reasoning far from mechanical roots, and this opens possibilities in his theory. Coulomb, in this regard, is a continuation of Hypinus' case, since he leaves mechanistic considerations untouched. Johann Euler's style of explanation is more rooted in his mechanical worldview, although he does produce mathematical formulae, he does mathematizes. Euler's explanation derives more from the ontology of his ether than from his mathematical results. Wrapping things up, Hypinus' style is more mathematical dependent and less mechanical. This contrasts with Euler's style, which is less mathematical dependent, although there is mathematics there, and more mechanical. There are at least two styles to use mathematics. This depends on their dependency on a mechanistic worldview. This shows two different styles of explaining and acquiring knowledge on the same phenomena. In Hypinus 1, the inferential conception captures the role of mathematics in the theory. In this case, mathematics is indispensable to the theory. In Euler's case, the map can sometimes be seen because he does mathematizes, but it is less relevant for the explanatory process since there's more dependency on a mechanistic reasoning. To answer our questions, we observed that there were indeed different types of mathematization in the electrical studies of the 18th century, and they depended on the importance of mechanical entities in the theory, if they were or were not the core of the theories. Nowadays, the style most predominant in physics seems to be Hypinus one, that is less mechanistic. However, our historical study shows that this was not the only possible scenario in the past. To make some further considerations about HPS, and we saw that in the study of mathematization, we see a fruitful ground for interactions between philosophy and history of science, because we can analyze the application of mathematics by philosophical lenses and then apply them to observe nuances and dependencies in historical cases, although we did make a linguistic choice in the beginning. As acknowledgements, I want to thank my advisor, Professor Cibelle Celestino Silva, and CAPS that financed this study. I will also like to thank my research group, which is the GHTC, Group of History and Theory of Science in the University of São Paulo. Thank you very much.